Okay, so here we're going to take a look at the power rule versus the exponential. But before we get into that, let's just revisit the power rule, and we're going to prove the power rule for any rational number. Excuse me, any real number. We previously, or in a first semester calculus, you've probably proved it for any rational number. But now we're going to expand it, right? So we're going to say if n is any real number. Real number. And f of x, excuse me, is equal to x to the n, then f prime of x is equal to n to the x to the n minus 1. All right, so now we're just going to take a look at it in the in terms of any real number, right? Previous proofs required the quotient rule, chain rule, right? Product rule, I believe, and then that n be some kind of rational number, right? But now we can actually expand this by you doing logarithmic differentiation, right? And that doesn't put any restrictions on what n can be, right? So we'll start off with y being x to the n, right? And applying our log to both sides, we get natural log of y to be equal to the natural log of x to the n. Powers of logs we can rewrite like this, right? ln of y. And now taking the derivative of both sides, right? Using the derivative like an operator, dx here. All right, again, on the left side of the equal sign, we're using implicit differentiation. So we get 1 over y times y prime. By the chain rule. All right, and here, n is just a constant, so we're taking derivative of natural log of x, which is 1 over x, or simplifying as n over x. And here, let's simplify here, and we get y prime multiply y from both sides. We get n times y over x, but again, y is just x to the n. So y prime equals n x to the n over x. Simplifying, we get our power rule, n times x to the n minus 1, right? Same as before. Am I saying, well, what's the big deal here? What's the catch here? The catch is really just that n is any rational number. So now this allows for a way to take the derivative of something like this if you needed to take the derivative of this. Right? The general power rule for any real number, any real number is bring the power, which is root 2, and then take the numerator, the exponent, and subtract it by 1. So we get something like this. All right. Okay. So that is the power rule for any real number. Now, here, as we move forward, we want to be able to distinguish here a common mistake, or not mistake here, common confusion here between students is these two functions, right, and applying the correct formula for each one of these, right? X to the n versus a to the x. So we want to be able to distinguish both of those and be able to use the proper formula, right? So there's really 4 cases that we have to look out for. So in general, that's 4 cases of just exponents and bases being constants versus variables or functions of x, right? The first one is when a and b are constants. So if I want to take the derivative of a to the b, right? Think of 4 to the 3rd power, 8 squared, right? Stuff like that. A and b are constants. Well, this, right, they're still constants. So we have the constant rule for derivatives. So that is always 0, right? That's the basic one, right? A and b are both constants, right? Again, think 2 cubed. right? 8 squared, etc., right? The derivative of those would be 0. Another case to watch out for is, right, our general power rule, where we have some function f of x, b, right? And then here we have b times f of x, b minus 1 times f prime of x, chain rule. Right here, think of functions like sine squared of x. Stuff like that, okay? Or x squared plus 3 to the 5th power, right? Or we have some kind of inner function that, it may just be x, right? It may just be, right, x to the 6th power, etc. All right, so all of those fall under this category here. All right, a third case is one where we have, now we switch it up, where we have our base to be a constant, right? But our exponent to be some power of, some function of x, right? So for something like this, we would do our formula, right? ln of a, natural log of the base, times the derivative of g to the x, and then here, a to the g of x. Right now here, think of something like 2 to the x, 3 to the root x, 5 to the cosine of x, or something like that. Okay, and now the fourth case, which the first three we've already done examples of, not necessarily in this class, but in our Math 1, and in case 3, we've done in this class. But the fourth case is, well, what if they're both functions of x? What if both the base and the exponent is a function of x? And in this case, I don't really have a general formula. This is going to take on the form of the logarithmic differentiation. Okay, so that is just really depends on what f of x and g of x are, what the form will look like. So let's actually do an example of those, right? We've done examples of those previous cases, but that fourth one is going to be something new, right? So our example here is, let's say I want to find y prime for y equals root x to the x power. Okay. All right. So again, this is something completely different than the power rule or even the general exponential, right? This is a function as the base raised to a function, in this case just x. All right. So we'll start off by, again, taking the natural log of both sides. So natural log of y, and here I'll start applying the power rule for logs, is x natural log root of x. And I'm also going to do myself a favor here, right? Natural log of x is just x to the 1/2. So I'm going to, again, apply the power, the exponent rule for natural logs in here. Let's write the intermediate step here. Bring that out in front. Again, this is all through the power of the natural logarithm and its properties, and we can see why it's useful, because here it simplifies my calculations. Right, so now let me take the derivative with respect to x here. All right, so on the left side of the equal sign, we'll get 1 over y times y prime, right? Chain rule here, our implicit differentiation. Here we're going to use the product rule, because I have two functions of x. So the first one, x over 2, the derivative of that is just 1/2, plus, leave x over 2 alone, and then the derivative of the natural log of x is 1 over x. Right? And you see why it's helpful to get the root out of there? Because if it wasn't there, I'd have to use the chain rule, right? So it just saved me a step, right? Excuse me, I'm 1/2 and then leave the other function alone, ln of x. Okay, all right, so now we have the product rule there for x over 2 times natural log of x. All right, and then simplifying this, right, I want to find y prime, so getting it by itself, we get y. And notice 1/2 is an exponent, right? Coefficient becomes an exponent inside the logarithm, so we get ln root x. Here the x is reduced to 1 plus 1/2, right? And we can leave it like this, or recall what is y equal to from our function. Y is root x raised to the x. Root x raised to the x. Okay, and here either of these I think are valid solutions here. Okay, and that is how we use logarithmic differentiation along with this with the exponential having a function in the base and the exponent.